Hey everyone, and welcome to another video on integral calculus. I'd like to pick up where we left off last time in the previous video, and where we were drawing some parallels between integral calculus and differential calculus. So just like in differential calculus, where we found the instantaneous rate of change, that is going from displacement to velocity, in integral calculus, we actually go the other way. So given a velocity function, we can find displacement. This is what we did in some of those problems in the previous video, that we had a function for velocity. Given a certain interval, we could find the displacement. Likewise, in differential calculus, we can find the slope of the tangent line at a point, right? Using the derivative, we can find slope of the tangent line. That's the geometric interpretation of the derivative. And the analogous geometric interpretation for the integral is area under the curve, right? And we saw how that's also calculated in the previous video. Now, what we're going to do in this video is we're going to take these two ideas a little further, and we're actually going to see some of the math behind how this is done and slowly go from there into sort of understanding the logic behind how we really get to what we call the integral today, right? So let's go ahead and get started. It's some pretty exciting stuff here, so let's go ahead and get started. All right, so this is the same problem that we saw somewhere a little bit towards the end of the previous video, right? The car's velocity is given by this function here. We want to calculate the total displacement after 10 hours. And if you remember, the problems we ran into were that because the velocity changes at every instant of time, we can't really use our displacement equals velocity times time formula to find that total displacement here. We also can't quite use the area under the curve idea like directly, because this shape is not something that we know how to find the area of exactly, right? Because if you look at it, it's not rectangular, it's not triangular. It looks a little bit like it could be triangular, but not exactly, and it's not quite circular either, because that's it doesn't quite have a circular path there. So what can we do then? Well, let's take a quick inventory of what tools we have available to us so far. So remember, the tools available that we have are displacement is velocity times time, which we talked about. And we also know that the area of a rectangle is width times height. Now, why do we use area? Why do we care so much about area of a rectangle? Well, it's because rectangles are nice shapes to work with, right? They're just intuitively, there's not a lot to them. Like, for example, with a circle, you have pi r squared. With a triangle, it's also not that hard, but you still have that 1/2 times base times height. With rectangles, it's very uncomplicated. It's just width times height. So that's why we like to use rectangles for this particular process. And our goal is to use these two tools to somehow look at a shape like this and find that area under the curve. So we're going to have to get a little bit creative, right? So we already know that it's not a rectangular shape, so we can't find it exactly, but let's just see if we can sort of approximate it using a rectangle, right? So let's take a look at what that might look like. And this is what that looks like. So my goal now is to use this rectangle to try and approximate this area under the curve, right? Because again, the rectangle is a very nice shape to find the area of. So if I can somehow get some kind of a rectangular shape that's very close to this area under the curve, that'll make my life easier to find that area. So all I did is I just drew this rectangle on top of this function here, and we're trying to see if that matches this area under the curve. Now, it does capture some of the area that we want, right? It does go down here a little bit, but we also have all this extra area over here that we don't want in our calculation, right? Because if I just take the area of this rectangle, that includes all this extra area that I'm not really interested in. So this is not a great representation for my area under the curve. But that doesn't mean the game is over yet. Let's try something else. What happens if I broke this up into two rectangles? Well, it's still possible. We saw an example last time where we had to use two different rectangles to find the area. And this is theoretically possible, and it looks better, doesn't it? Because, well, there's still a lot of extra area here, right? There's still a lot of extra area here, but this is a much better representation for that area under the curve because, well, a lot of that extra area has been eliminated, right? So this is looking a lot closer to this area under the curve than the previous approximation. So let's try this one more time. Now I've done the same thing, but with 5 rectangles. Now you can see this is a really, really good approximation, actually, a really good approximation for this area under the curve, right? Or a really good representation for this area under the curve. So it's very, very close to this actual area here, and the amount of extra stuff here, that's sort of the amount of extra area here that I'm calculating, is minimal. It's not as bad, right? And so you could add even more rectangles if you want. You can do like 10, 15, 20, how many ever you want, and eventually you'll get a really, really good approximation for what this area is, right? And again, why do we use rectangles? Well, the rectangle is a very nice shape to find the area of, right? So it's really, really easy for me to find the area of these 5 rectangles and just add them together, right? Because if you tell me how high this rectangle is, how wide the rectangle is, I can just very easily just multiply those together and then add up the areas for all these rectangles, and that gives me the area. So that's why this is a very useful approach. All right, so now that we've seen this in action, let's go ahead and actually put this into a little bit more math-like terms, just so that we can actually use it. So let's see if we can put some things to this let's put some variables to these different things. So firstly, what can we say is the width of these rectangles? Well, let's just choose a variable for our width, right? So I'm going to call the width delta x. And what's important here is I'm going to make delta x the uniform width for each rectangle, right? So we're going to say the width is delta x, and this guy is going to be the same for all the rectangles. Now, this is not a mandatory thing, but it makes our math easier, right? Because we can define the width of this rectangle to be whatever we want it to be. So we want to just make all the widths the same, right? It makes a lot of the math much nicer. Now, what about the height for the rectangle? Well, what determines how tall this rectangle should be? Well, it's going to be the function itself, right? So we can use that function as a definition for how tall I want my rectangle to be. So, for example, you can call that f of x sub 1. That's how tall the rectangle that's how tall this first rectangle has to be. Likewise, we can call this height here f of x 2. That's how tall that second rectangle has to be, right? And so, therefore, we can just say our height is just going to be f of x sub I. And the reason we do f of x sub I is just because that height will change for each rectangle. So this is the height of the ith rectangle. So for any arbitrary rectangle, the height would be f of x sub I. Right? Now, okay, I have my width and my height. Now, to get my area, all I need to do is multiply these two things together and then add for each rectangle, right? So all I have to do now is I can say, all right, so my area is going to be delta x times f of x sub 1 plus delta x times f of x sub 2, and so on and so forth, right? And if I wanted to be a little bit fancy here, I could use summation notation and say the following. So this area is going to be the same thing as the sum. This is what we call sigma, right? The sum from I equals, not 0, it should be I equals 1 to n, right, where n is my number of rectangles. That can be whatever you want, of f of x sub n, x sub I, excuse me, f of x sub I times delta x. Now, don't get scared by this summation notation. All this is saying is the same thing as this, right? So we take for I equals 1 to n, we take f of x sub I times delta x. So we go f of x sub 1 times delta x, and then we add f of x sub 2 times delta x, and then we could even go further. We could say delta x times f of x sub 5 times 3, 4, 5, how many ever we need to do. Right? So that's basically what this thing is saying to us. So putting it all together, so this is our final formula here. So we have the area is the summation from I equals 1 to n, f of x sub I times delta x. This is what you'll probably see in your textbooks. With the minor addition, you'll probably see f of x sub x with a star here. Again, that doesn't affect our day-to-day calculations, but it's just a bit of notation to make this mathematically rigorous. But yeah, that's basically what we end up with. So what does this actually tell us? Well, this tells us that given n rectangles, like we saw before, if we put n rectangles under this curve here, this formula will tell us the approximation for area under the curve. What this is doing, it's going to take the height of each of those rectangles, multiply it to the uniform width, and add everything together. Right? That's all it's doing here. We're multiplying and then adding. Right? So that's basically it. And in the next video, we'll go over some problems we can solve with this formula, and then later on we'll talk about how this actually relates to the actual integral. Right? So that's it for this video. If you found this video helpful, please do like, share, subscribe, leave a comment, and check out some other videos. See you next time!